Have you ever stopped to think about how the world around us is even built? I mean, really built. Well, it all comes down to a kind of hidden drama happening at the atomic level. A story of giving, taking, and a really powerful attraction. Today, we're going to pull back the curtain on the atomic handshake that creates something we call ionic compounds. And believe it or not, our story starts with something you've definitely got in your kitchen right now. So, what's the big secret hidden inside a single, tiny grain of ordinary table salt? What makes it, well, salt? So, here's the secret. It's this incredible, beautiful crystal structure. Do you see how the positive and negative charges are all locked together in this perfect, orderly pattern? That intense attraction is the absolute heart of what an ionic compound is all about. Here's how we're going to break it all down today. First, we'll get into the give and take between atoms. Then, we'll check out the unique properties these compounds have. After that, we're going to learn their language, how to name them and write their formulas. And stick around because at the end, there's a little plot twist with some special metals. Okay, first up, the give and take. Let's dive into the fundamental interaction that makes this whole thing possible. So, first things first, you gotta meet our main character, the ion. And an ion isn't some super complicated thing. Nope, it's just a regular atom that's either gained or lost an electron, which gives it an electrical charge. And what happens when you get a positively charged ion near a negatively charged one? Well, you know what they say, opposites attract. That powerful, almost magnetic pull is what forms an ionic compound. So here's the deal, and it's a super simple formula to remember. In this atomic handshake, you've almost always got a metal and a nonmetal. The metal is the generous one. It's the giver. It gives away an electron. The nonmetal is the taker. It happily snags that electron. And that single exchange is what creates those positive and negative ions to begin with. Okay, so this atomic handshake, it creates a seriously strong bond. But what does that actually mean? Like, what's the personality of these compounds because of it? Let's find out. Well, they have some really distinct, kind of fascinating traits. For starters, they're usually hard, brittle solids at room temperature. That's why salt is a crystal, not a puddle. They form these beautiful, perfect crystals with flat sides. They also have incredibly high melting points. And here's a really cool one. They can conduct electricity, but only when you dissolve them in something like water. So why? Why are they like this? It all comes back to this image, that super tight alternating pattern of positive and negative ions. This crystal lattice is so strong, which makes them hard and gives them those high melting points. But if you tap it just right, that perfect pattern shatters, and that's exactly why they're brittle. Now that we know what they are, let's learn how to speak their language. It's time to figure out how to name these compounds, and honestly, you'll be surprised how easy it is. Seriously, there are just 3 simple steps. That's it. First, you just say the name of the metal. Second, you say the name of the nonmetal. And third, for the nonmetal, you just chop off the ending and change it to "ide." Done. All right, your turn. Let's do a quick pop quiz. Take a look at this compound right here, AlCl3. Using those rules we just learned, what would you call it? Let's break it down. Al is the metal, that's aluminum. Cl is the nonmetal, chlorine. So we take chlorine, change the ending to "ide, and it becomes chloride. Put them together, and you get aluminum chloride. See? Simple as that. All right, we've gone from formula to name. Let's flip it around. Now we're going to write the chemical recipe, the formula. It's all about getting the proportions just right. And luckily for us, chemists have this awesome little shortcut for it called the crisscross method. It's a really simple visual trick that helps you figure out exactly how many of each atom you need to make sure all those positive and negative charges cancel each other out perfectly. Now, to use this trick, you first have to know the charge of the ions. And for that, the periodic table is basically our cheat sheet. For a lot of these elements, their group number on the table gives you a huge clue about what charge they'll form. Like everything in group 1 loves to form a +1 ion, while everything over in group 17 forms a -1 ion. Let's just take a look at these common ones. Let's walk through one together. Magnesium oxide. Step 1, write the symbols, Mg and O. Easy. Step 2, find their charges from the table. Magnesium's a +2, oxygen's a -2. Step 3, you take those numbers, just the numbers, not the plus or minus, and you crisscross them down. That gives us Mg2O2. But here's the final, crucial step. You have to reduce the numbers if you can. Since we have a 2 and a 2, we can simplify that down to just MgO. All right, you're getting the hang of it, right? But just when you think you've got all the rules down, chemistry throws us a curveball. It's time for the plot twist, the special metals, the rule breakers. So here's the twist. Some metals, and these are mostly the ones we call transition metals that live in the middle of the periodic table, well, they're a little flexible. We call them multivalent, which is just a fancy way of saying they can form more than one type of positive ion. Iron, for example, can be a +2 or a +3 ion.
So how in the world are we supposed to know which charge the metal is using? It's all in the name. Just look at this comparison. For a standard compound like sodium chloride, the name is just the name. But for one with a multivalent metal, like iron phosphide, you see that Roman numeral in there? That is our big clue.
And this right here is the golden rule. It says it perfectly. We use a Roman numeral in the written name only to show which charge the metal is using. That number, the 3, tells us we're dealing with the iron 3+ ion, not the 2+ version. It's a critical piece of information that only goes in the name, never in the formula itself.
So there you have it. We've seen how this simple give and take between atoms creates this incredibly strong ionic bond, building everything from our table salt to precious gemstones. It kind of makes you wonder, right? If this is the relationship for the givers and takers, what other kinds of chemical relationships are out there, holding our entire world together?